In the south of Denmark, a mega project is underway to build a tunnel under the Baltic, linking the country to Germany.
They said it was impossible. Engineers laughed. Politicians walked away. And yet, someone decided to bury a tunnel beneath one of the most unforgiving stretches of ocean on the planet. 18 kilometers of freezing, brutal sea, and they thought, let's just go through it. 7 billion euros. 89 monstrous concrete blocks.
It's not only linking Denmark to Germany, it's linking Scandinavia to Central Europe. Everybody's the winner because obviously businesses, they will be closer connected. And then by not having an extra distance to drive, you will also cut in carbon because traveling 160 kilometers less.
A construction process so insane it had never been attempted at this scale before. And the result? The longest undersea tunnel ever built. But here is what nobody is talking about. There is a stretch of water in northern Europe that has quietly shaped the way people, goods, and trains move between Germany and Denmark for centuries. It is called the Fehmarn Belt, and it spans roughly 18 kilometers of the Baltic Sea, sitting between the German island of Fehmarn and the Danish island of Lolland. To most people glancing at a map, it looks like a small gap. In practice, it has always been a significant obstacle. For a long time, the only way to travel by land from Germany to Denmark was to go the long way around the Baltic Sea. That means heading north through Germany, crossing into Denmark via the Jutland Peninsula, and then making your way east and south again to reach Copenhagen or any other destination on that side. Depending on where you start, that detour can add several hundred kilometers to a journey that should, geographically speaking, be quite short. It is a bit like living across the road from someone and having to walk around the entire block just to knock on their door. Eventually, a ferry service was introduced to bridge that gap. Today, a ferry crossing takes around 45 minutes, which is a reasonable solution for cars and passengers. It works well enough for road traffic, but it creates a persistent problem for rail. Trains cannot simply hop on a ferry in the same way. Every rail journey between Germany and Denmark still has to take the long overland route, which adds time and cost to freight and passenger services alike. For a region that considers itself one of the most well-connected in the world, this has long been considered an embarrassing gap in the infrastructure. Discussions about doing something more permanent about the Fehmarn Belt crossing began picking up momentum in the 1990s. At that point, a fixed link of some kind started to seem not just desirable, but genuinely necessary, particularly as trade and travel between Scandinavia and the rest of continental Europe continued to grow. The question was not really whether to build something, but what to build. The most obvious answer, at least on the surface, was a bridge. Bridges have been built across far wider stretches of water, and there is already a successful precedent nearby. The Øresund Bridge, which connects Copenhagen in Denmark to Malmö in Sweden, opened in the year 2000 and has been a considerable success, both economically and practically. It seemed reasonable to assume that a similar structure across the Fehmarn Belt might work just as well. However, feasibility studies told a more complicated story. The ground conditions beneath the Fehmarn Belt are not ideal for a bridge of that scale. The seabed composition, combined with the sheer length of the crossing, would make a bridge extraordinarily expensive to build and maintain. Engineers and planners looked at the numbers carefully and concluded that while a bridge was technically possible, the cost and complexity pushed it into territory that was difficult to justify. A bridge was taken off the table. That left a third option, one that is less commonly known to the general public, but has been used successfully in various parts of the world since the mid-20th century. The solution is called an immersed tube tunnel. The basic principle is more straightforward than it might sound. Instead of drilling through the seabed, as you would with a bored tunnel, an immersed tube tunnel involves digging a trench along the floor of the sea, manufacturing large concrete. Tunnel sections on land, floating those sections out to the correct position, and then sinking them into the trench one by one, before connecting them together to form a continuous underwater passage. Once the tunnel sections are in place and connected, the trench is covered over again. It is a method that has been used for crossings in places like the Netherlands, Japan, and the United States, and it is generally considered to be more cost-effective than boring when the water is not too deep and the distance is significant. For the Fehmarn Belt, with its relatively shallow waters and its 18-kilometer span, the immersed tube method was determined to be the most practical and economically sensible choice. And so, after years of planning, political negotiation, environmental assessment, and public debate, the Fehmarn Belt Fixed Link project was formally approved. Germany, Denmark, and the European Union committed to funding what is now described as a €7 billion project. Construction officially began in 2020, and the tunnel is currently scheduled to open in 2029. When it does open, the impact on travel and transport in the region will be considerable. The tunnel will carry 3 lanes of road traffic in each direction, which alone would represent a significant upgrade over the existing ferry service. But perhaps more importantly for the long-term economic case, it will also carry rail lines in both directions. That means high-speed passenger trains and freight services will finally be able to travel directly between Germany and Denmark without the detour that has defined this route for so long. The numbers that are being quoted in relation to journey times are striking. A car crossing through the tunnel is expected to take around 10 minutes. A train will complete the crossing in approximately 7 minutes. To put that in perspective, the ferry currently takes 45 minutes under good conditions, and that is before you factor in the time spent waiting to board, loading, and unloading. The fixed link will not just be faster, it will be fundamentally more reliable, operating regardless of weather conditions that can sometimes delay or cancel ferry services. The tunnel itself will be the longest immersed tube tunnel in the world once it is completed. It will stretch the full 18 kilometers of the Fehmarn Belt, sitting on the seabed and connecting the 2 islands on either side. The scale of the engineering involved is difficult to fully appreciate without seeing it in person. But every part of the construction process, from the manufacturing of the tunnel elements to the marine work required to place them on the seabed, is being carried out at a level of precision and ambition that puts it among the most significant infrastructure projects currently underway anywhere in Europe. The manufacturing process for the tunnel elements is taking place entirely on site, at a purpose-built facility on the German side of the crossing. The tunnel is made up of 89 elements in total, consisting of 79 standard elements and 10 special elements. Each of these elements is not delivered or transported from somewhere else. They are being built from scratch, right there at the water's edge, in a facility that was itself constructed specifically for this project. That fact alone gives some indication of just how large and complex this undertaking really is. Walk into the facility where the Fehmarn Belt tunnel elements are being manufactured, and the first thing that strikes you is the scale. This is not a construction site in the traditional sense, where you might picture workers laying bricks or pouring concrete into relatively modest forms. This is something closer to an industrial production line, one that has been designed and built from the ground up with a single purpose in mind. Every machine, every hall, every process happening inside this facility exists solely to produce the 89 tunnel elements that will eventually sit on the floor of the Baltic Sea. The process starts, as so many large concrete structures do, with steel. Concrete is an exceptional material in many ways. It is strong, durable, relatively affordable, and it can be shaped into almost any form you need. But it has one well-known weakness. It handles compression well, meaning it can bear enormous loads pressing down on it, but it performs poorly under tension, which is the kind of force that tries to pull or stretch it. Left on its own, concrete under tension will crack. For a tunnel sitting on the seabed and subject to the forces of the ocean, that is obviously not acceptable. The solution, as with most large concrete structures built in the modern era, is to reinforce it with steel. The reinforcing steel arrives at the facility in large bundles, delivered by ship in batches of around 5,000 tons at a time. From the moment it arrives, it enters a carefully organized process that will eventually transform it into the dense, intricate cages of steel that form the structural skeleton of each tunnel segment. The first stage of that process takes place in a dedicated steel fabrication building, a space covering approximately 18,000 square meters, which gives some sense of how much material is being handled at any one time. Inside that building, the raw steel is fed into machines that weld the individual bars together in precise configurations to create prefabricated panels. These panels are not just a rough approximation of what is needed, they are engineered to exact specifications, with intermediate layers spaced at consistent intervals to ensure the correct level of structural stiffness throughout the finished element. The machinery used for this welding process was not bought off the shelf. It was developed specifically for this project, a detail that underlines how unusual and demanding the requirements of this particular build actually are. Once the panels have been fabricated, they move out of the steel building and into the production halls where the real assembly work begins. There are 5 production lines operating within the facility, and each one follows the same sequence of steps. The process begins at the floor level of the tunnel segment, where the steel panels are laid out and assembled into the base of what will eventually become a full rebar cage. A rebar cage, for those unfamiliar with the term, is essentially the steel framework that sits inside a concrete structure. When the concrete is poured around it, the steel and concrete work together, with the concrete providing resistance to compression and the steel handling the tensile forces. Watching one of these cages being assembled makes it easier to understand why the production facility had to be built on such a large scale. Each tunnel element is ultimately made up of 9 individual segments. A single segment is already a substantial structure, but 9 of them joined together form an element that is truly immense. The production line is configured so that the floor of a segment is assembled first, then the prefabricated wall sections are lifted into position and connected to the floor. And finally, the top section is added to complete the box shape. At that point, you have a full rebar cage for one segment, an open steel skeleton that will eventually be encased in concrete. Running through the structure at various points are hollow tubes. These are not part of the rebar cage itself, but serve a specific purpose that will become important later in the process. They are designed to accommodate tensioning cables, which will be threaded through after the concrete has been poured and cured. The cables are then put under tension, which has the effect of compressing the concrete segment from within, counteracting the tensile forces it will be subjected to once it is in position on the seabed. Once the elements have been placed and settled into their final positions on the ocean floor, the tension in these cables is actually released, allowing the segment a small degree of relaxation and flexibility. It is a precise and deliberate engineering choice, not an afterthought. One of the more interesting aspects of how these elements are put together is the decision to manufacture them in 9 separate segments rather than as a single continuous pour. There are practical reasons for this. Pouring the entire length of a tunnel element in one go would require an extraordinary amount of concrete to be placed at once, which would create significant challenges around quality control, heat management during curing, and the sheer logistics of the pour itself. Breaking it into 9 segments makes each individual pour more manageable, while still producing a structure of the required size and strength. But there is an engineering benefit to this approach that goes beyond just making the construction process easier. By manufacturing each element in segments with joints between them, the finished element is not a completely rigid structure. It has a degree of flexibility built into it. Each joint acts as a point where the element can accommodate slight movement without cracking or failing. When you then consider that the full tunnel is made up of 89 elements, each with 9 segments, you end up with a total of 711 segments connected by flexible joints running the entire length of the crossing. This means the tunnel, rather than being a single inflexible tube sitting on the seabed, behaves more like a chain, able to respond to ground movement or pressure without being damaged by it. Once the rebar cage for a segment has been assembled, it moves into the casting hall, where the concrete is poured. The casting environment is carefully controlled, and the reason for that level of control comes down to the nature of concrete itself. When concrete cures, it generates heat as part of the chemical reaction taking place within it. If different parts of the structure cure at different rates, or if the temperature in the casting hall varies significantly from one pour to the next, it can create inconsistencies in the finished concrete that compromise its long-term strength and durability. To prevent this, the facility is equipped with a climate management system that uses a network of ducts to distribute either warm or cool air throughout the hall as needed. The goal is to ensure that every single pour takes place in as close to identical conditions as possible, regardless of what the weather is doing outside. After a segment has been cast and has cured sufficiently, it is slid along the production line to make space for the next segment to be poured. This sliding process continues, one segment at a time, until all 9 segments that make up a single element have been poured. By the time the 9th segment has been cast, the first segment of that element is already outside the building, and the full element is gradually emerging from the production hall like something being slowly pushed out into daylight. Before an element can be moved toward the water, there is one more critical piece of work to be completed. At each end of the element, a steel ring is fabricated and fitted around the perimeter. This ring serves as the mounting point for what is known as the Gina gasket, a rubber seal that runs all the way around the end face of the element. When two elements are eventually brought together on the seabed, the Gina gaskets on their facing ends are pressed together and a vacuum is applied between them. The vacuum draws the two elements tightly against each other, compressing the rubber gaskets and creating a watertight seal that will hold for the lifetime of the tunnel. It is a system that has been used in immersed tube tunnels elsewhere in the world and has a strong track record, but at the scale of the Fehmarn Belt project, the precision required to make it work consistently across 89 elements and over 18 kilometers is considerable. At this stage of the process, the elements are sitting on land, enormous concrete structures that weigh in the region of 73,000 tons each. Getting something of that size from a production facility on shore to a precise position on the floor of the Baltic Sea requires a sequence of operations that is every bit as carefully planned as the manufacturing process itself. That transition, from land to sea, is where the next phase of the project begins. At some point in the manufacturing process, the focus shifts. The work inside the production halls, the welding, the assembling of rebar cages, the carefully controlled concrete pours, all of that has served one purpose: to produce tunnel elements that are structurally sound, precisely dimensioned, and ready to make a journey that very few man-made objects have ever had to make. The challenge that comes next is one of the most logistically complex parts of the entire project. How do you take an object weighing around 73,000 tons and move it from dry land to a specific location on the floor of the Baltic Sea, accurately enough that it connects with the elements already placed on either side of it? The answer involves a sequence of steps that begins right at the edge of the production facility and ends somewhere beneath the surface of the sea. Each step has to be executed with a level of care and coordination that reflects just how little room there is for error. A tunnel element that is placed even slightly out of position could compromise the watertight integrity of the connections between elements, which is something that cannot be allowed to happen in a structure that will carry cars and trains under the sea for generations. The first part of the journey for a finished element involves moving it from the production line into an area known as the dry dock. This is a large enclosed basin sitting directly adjacent to the production facility, and it is where the elements spend some time receiving final preparations before they are introduced to the water. Workers carry out inspections and finishing work on the elements while they are still sitting on dry land, checking that everything is in order before the next and most visually dramatic stage of the process takes place. Each element, before it can be floated, needs to be sealed at both ends. Large temporary structures called bulkheads are fitted across the open ends of the element, making it airtight. This is essential because the principle that allows a 73,000-ton concrete structure to float is the same principle that allows a ship to float. Despite its enormous weight, the element is not solid. It is hollow. The interior space enclosed by the concrete walls, floor, and roof of the element contains a large volume of air. When the element is sealed and introduced to water, that trapped air gives it enough buoyancy to float. The bulkheads are what keep that air inside, and they have to be fitted and secured with complete reliability before any water enters the picture. Once the bulkheads are in place and the preparation work is complete, the dry dock is sealed off using a large, movable gate. This gate closes across the entrance to the basin, separating the elements from the open water on the other side. Then water is slowly pumped into the dry dock. As the water level inside the basin rises, it gradually reaches and then surrounds the base of the elements. At the point where the water level is high enough, something that is hard to fully appreciate until you see it happens. Those enormous concrete structures, each one heavier than most things that have ever been built, begin to lift off the ground and float. It is a moment that sits at the intersection of basic physics and serious engineering. The mathematics behind it are well understood, and the process has been used in immersed tube tunnel projects around the world. But the scale at which it is happening here, with elements of this size and weight, makes it feel remarkable, regardless of how familiar you might be with the underlying principles. The dry dock at the Fehmarn Belt facility is designed to handle 2 elements at a time, which means that on each occasion the flooding sequence takes place. 2 of these vast structures are rising off the floor of the basin simultaneously. With the elements floating inside the sealed dry dock, the next step is to bring them out into open water. Tugboats enter the picture at this stage. These are the workhorses of any large marine construction project. Compact and powerful vessels that are capable of maneuvering objects many times their own size through confined spaces with considerable precision. The tugboats attach to the floating elements and begin guiding them out of the dry dock and into the deeper water of the work harbour. The work harbour is an intermediate stop in the journey from the production facility to the seabed. It is here that additional preparation work takes place before the elements are ready to be towed to their final position. One of the things that happens in the work harbour is the addition of ballast. When an element is first floated out of the dry dock, it is sitting relatively high in the water because it is full of air and has nothing weighing it down beyond its own structure. Before it can be sunk to the seabed in a controlled and precise manner, its buoyancy needs to be carefully adjusted. This is done by adding weight, which brings the element lower in the water and allows the sinking operation to be managed with the accuracy that is required. The work harbour is also where the element undergoes its final checks before the tow out to the tunnel alignment begins. The tunnel alignment is the term used for the route along the seabed where the tunnel is being constructed, and every element has a specific position within that alignment that it needs to occupy. The placement of each element is not approximate. It has to be exact because the Gina gaskets at the ends of the elements need to make proper contact with the gaskets on the elements already in place, and the vacuum system that creates the watertight seal between them depends on the two faces being brought together with precision. When an element has been cleared for tow out, the tugboats take it from the work harbour and begin the journey out to sea. This is a slow and careful operation. The element, despite floating, is not easy to control in open water. It is extremely large, it has no propulsion of its own, and it is affected by currents, wind, and wave action. The tugboat crews responsible for these tows are experienced in handling large marine objects, but each tow out is a significant undertaking that requires close monitoring of the weather and sea conditions. Operations are planned well in advance, and there are clear criteria in place for when conditions are acceptable and when a tow out needs to be postponed. Once the element reaches the tunnel alignment, the process of lowering it to the seabed begins. This is done by gradually flooding the interior of the element in a controlled way, replacing the air inside with water. As the buoyancy decreases, the element sinks. The rate at which this happens is managed carefully, and the element is guided into position by a combination of the tugboats and a specialized installation vessel that provides the precise positioning capability needed for the final stages of the descent. Measurements are taken continuously throughout the sinking process to ensure the element is tracking correctly toward its intended position. When the element reaches the seabed and comes to rest in the trench that has been prepared for it, the connection to the adjacent element can begin. The open face of the newly placed element is brought into contact with the face of the element already in position. As the two Gina gaskets touch and are pressed together, a vacuum is applied to the space between them. The vacuum draws the elements tightly against each other, compressing the rubber, seals, and eliminating any gap through which water could enter. At that point, the water that has accumulated in the small space between the two elements, the so-called joint recess, can be pumped out, and the interior connection between the two elements can be made permanent. The trench around the newly placed element is then backfilled, and the process begins again with the next element waiting in the work harbour. Across 89 elements and 18 kilometres of Baltic seabed, this sequence is repeated until the last element is in place and the tunnel is complete from one shore to the other. What is being built here is more than just a piece of transport infrastructure. The Fehmarn Belt fixed link represents a significant shift in how Northern Europe is connected. When the tunnel opens, expected in 2029, it will bring Germany and Denmark closer together in a way that goes beyond the simple reduction in travel time, though that reduction is substantial. Freight that currently has to travel hundreds of extra kilometers by road or rail will be able to move directly through the tunnel. Passenger trains will run between Hamburg and Copenhagen far faster than they do today. The economic relationship between Scandinavia and the rest of continental Europe will operate on a different footing, with a direct fixed link where there was previously only a ferry crossing or a long detour. The engineering that has made this possible is the product of decades of accumulated knowledge about how to build in and under the sea, combined with a level of ambition that has pushed the boundaries of what immersed tube tunnel construction has previously achieved. The Fehmarn Belt Tunnel will be the longest of its kind in the world, and the processes developed and refined during its construction will likely influence how similar projects are approached in the future. It is, in the most straightforward sense of the phrase, a record-breaking piece of work, and the stretch of water that has separated these two countries for so long is finally going to have a permanent answer sitting on its floor.